Okay, in this video, I'll be going over the exam 3 study guide. Okay, for number 1 says, in a 0.40 molar solution, the weak acid ammonium, NH4 plus, is 5% dissociated. Find H3O plus concentration, pH, OH minus concentration, pOH, and the weak acid's Ka value. So let's start off with the pH, pOH, H3O plus, and OH negative concentrations. So for that, we want to find out how much of the acid actually dissociates. So it says the acid is 5% dissociated. So we just want to multiply the starting solution, which is 0.4 molar, by 5%, which is 0.05. And that should give you a concentration of 0.02 molar. That's actually going to be the concentration of hydronium ions. Because the weak acid dissociates this much, that means like it breaks apart to form like that much acid, you know? It's kind of how you want to see it. Like the percent dissociated is also like the percent or like the molarity or concentration of acid or base created. So with this, we're gonna find our pH. Or we could box this too, since this like is one of our answers. So pH is just the negative log of your hydronium concentration, which is 0.02. Let's put that off to the side. pOH is just your Kw, which is 14 usually, minus your pH, or sorry, it's pKw, minus your pH. So 14.00 minus whatever we'll get from here. And your OH concentration is just going to be your, what's it called, 10 raised to the negative of whatever you get for your pOH right here. So let me go ahead and calculate this real quick. So doing all that gives us a pH of 1.70, a pOH of 12.3, and a hydroxide concentration of 5.01 times 10 to negative 13 molar. So this will be your answer for that first part. So solving for the K requires the ice table. Because remember, Ka is the concentration of hydronium ions times the concentration of what's it called, your conjugate base, over the concentration of your acid. So NH4 plus aqueous reacts with water. Good. To make its conjugate base, which is just ammonia, and our acid, which is hydronium, our conjugate acid, I mean. We try to fit this all in one thing. But the gist of this is that we can use our previous hydronium concentration as x. So, sorry, maybe 0, 0, plus x, plus x, x, x. And since our hydronium concentration was solved for in the previous part of this problem, we're going to use that. So 0.02 molar. And that we are x for this one as well, 0.02. Right? Yeah, that's right. Since water is liquid, we don't count that. No, sorry, I forgot this part. And the starting concentration of our ammonium is 0.40 molar. It's minus x. But x is 0.02, so we just subtract. So I'm not gonna do the math. I'm just gonna show you the answer hit. This is pretty easy. That. So our Ka is our hydronium concentration times our conjugate base over our acid concentration. So since they're the same thing, we can just square the 0.02 molar, and we just divide it by 0.38. That'll give me a Ka of 1.05 times 10 to the negative 3, which is going to be your answer. So it's kind of how you find the Ka. And if you were given, like I said, if you were given a generic weak acid, you would use these variables instead. So your conjugate base would be this. Oh, sorry, this is wrong. There's no negative sign there. Actually, there is. So your conjugate base would be ammonium. Hydronium stays the same, and your acid would be what you start off with. And water is always water. When you work with like weak acids dissociating, it always reacts with water because stuff dissociates in water. And that's it for this problem. Number 2 says stomach acid's pH typically ranges from 1.50 to 3.50. If stomach acid's pKw is 14.00, what is its range of hydronium concentration and hydroxide concentration? So we're getting pH, a range of 1.50 through 3.50. So from this, we can easily get a range of hydronium concentrations. Remember, to solve for hydronium concentration, you just raise 10 to the power of whatever your pH is. So I'll do that first. So it's 10 up to the negative power. I forgot to say negative, I think. Okay, so we'll leave that alone. Now let's do the second one. 10 to the negative 3.5. That's good. Now for the hydroxide range, we could use the concentration we saw for the hydroxide concentration, but I prefer just finding the pOH and going from there. But you could do either or. Doesn't matter. So we're given a pKw of 14.0, and it will usually be 14.00 unless stated otherwise. So from that, we subtract our pHs. That one should be like 12.50. And our second one should be I think like 10.50. They should be right. Okay, so for the hydroxide range, it's the same as pH range. We bring 10 to the negative of whatever our pOH is. 12.50 should give us something. And for our second one, it's to negative 10.50. So doing all that should give you the hydronium range of 0.0316 molar to 3.16 times 10 to the negative 4 molar. And the hydroxide range of 3.162 times 10 to the negative 13 molar. And 3.162 times 10 to the negative 11. I don't know why these numbers are so similar to each other, but it's fun. So for your answer, I put like H3O plus range and be like 0.0316 molar to 3.16 times 10 to the negative 4 molar. Box that. Onto that. So just like that. And this should be it for this problem. So this is pretty easy. I don't think I really have to explain much here. You just find hydronium and hydroxide concentrations from pHs and POHs. And on the exam, I'd watch out for the pKw because it might change on the exam. It won't be 14. Or it might not be 14. I can't say for sure, but yeah, this should be it. Okay, number 3 says, which of the two acids is stronger? So we're given a pair of acids. We want to figure out which one's stronger. So the first one is H2SeO3 or H2SeO4. So the general rule for like figuring out acid strength is if it's like an oxyanion like this that has like a nonmetal and some number of oxygens like greater than 2, I think 2 or 3. For those you want to see which one has more oxygens attached to it basically. And you can see that one has 4 oxygens right here. This one has 3. So it'd be this one that's stronger. And there's a explanation for this, but I'm not really sure to be honest. But I think it's something like this. Something like this. And this makes like what's it called? This gives you like more electrons, I think, that are readily available to react or something. I'm not really sure to be honest, but just like see which of the two has more oxygens attached to it. If it's an oxyanion, if it's like a nonmetal with like oxygens attached to it, kind of like this, or like phosphate PO4 or sulfate. These are oxyanions. So for those, you want to see which one has more like oxygens attached to it, like I said. So B is phosphoric acid. Pretty sure that's what it's called. And H3SO AsO4. So these are oxyanions, like the last problem. See, there's oxygens attached to it, but there's different non-metal species right here. So for this, you want to see which one is more like electronegative, basically. So if you look at like a periodic table, electronegativity goes, it increases as you go up the periodic table and as you go across to the right on the periodic table, which means the most electronegative thing is fluorine. So basically, which of these two nominals is higher up on the periodic table? If you look at it, it's phosphorus. So the more electronegative species makes the stronger acid. That's how I would like look at it, I guess. And for C, it's H2S or H2TE. For this one, you might say that sulfur is more like electronegative than what's it called? Tellurium here. I think that's what it's called. And while that's true, you shouldn't look at it like that for this case because another like factor that plays into acid strength is atomic size. So the what's it called? The smaller it is, like the atom size it has, the stronger the acid. And like I said, there's probably like an explanation for this, but I have no idea. Just trust me, bro. And so you see, sulfur is larger than tellurium, which means this one, this H2TE, is a stronger acid. And you can search up like what the rules are for acid strength, but these are kind of like what's it called? Like really general. They're kind of like really simplified. So just to like reiterate, you want to, for what's it called, for oxy ions, you want to see which one of the two has more oxygens attached to it. The one with more oxygens is a stronger acid. If the number of oxygens attached to the oxyanion are the same, like how you saw here, then you want to go towards like electronegativity. The one with the highest or the higher electronegativity makes the stronger acid. And if it's not an oxyanion like this, like for C, for instance, you want to look at like atomic size. You know, the smaller the atom, the closer they are, which means the more polar they are, basically. I guess that's one way to put it. Which means they make a stronger acid because of it. And that should be it for this problem. Number 4 says, what is the pH of 0.26 molar aniline? It's got a Kb of 3.9 times 10 to the negative 10. I just realized I didn't give you guys the formula for aniline, but it's C6H5 um, and H2. So this is going to react, or I mean dissociate in water. It's going to get a hydrogen from water and gain a positive charge. So C6H5 NH3 plus equals, and that's going to make water turn into hydroxide. So from this, we want to solve for hydroxide concentration, because from there, we could turn that into a POH. Different POH, we could turn that into a pH. Yeah, you get me? So let's start with the ice table. And before we do anything, we want to see whether this like follows the, what's it called? The simplifying assumption. So to do that, we divide our starting molarity of aniline, which is 0.26 molar, by our Kb, which is 3.9 times 10 to the negative 10. So this should kind of be obvious, but this is going to give us a number way higher than 400. So just find that real quick. So it gives me like what? 6.7 times 10 to the 8th, I think. So obviously this is greater than 400, which means we can use the simplifying assumption, which means the change here, the change in x here, is going to be basically 0. So we can use, or we can treat our starting molarity 0.26 molar as our final molarity. So 0.26, it's about 0.26 molar, okay? Water doesn't count because it's a liquid. And here it's going to be 0, 0, since we don't start off with anything. But read positive x, x, and x. So we want to solve for x. So to that, we want to set up our Kb equation. So here it'll be x squared because it's products over reactants, which is this 0.26. So you guys should know this already. We did this like a bunch in lecture. So I'll skip over this. Actually, no, I won't skip over it actually. But let me see how do I do this. So x squared equals Kb times 0.26, and x is equal to the square root of Kb times 0.26. So let me just do that for you real quick. So Kb 3.9 times 10 to the negative 10 times 0.26 I should give us a number of 1.0 times 10 to the negative 5 molar. So that'll be our x. So we're going to replace our x's here with that. So 1.0 10 to the negative 5 molar. 1.0 times 10 to the negative 5 molar. I guess you don't gotta do this part since it's not required. You just have to find the OH. But you're just doing it like along the way anyways, so you might as well. So now we find our POH. So it'll be our negative log of a concentration, which is 1.0 times 10 to the negative 5th. And that should give us a pH of 5. But we'll add on 2 zeros because that's how pH kind of like is supposed to be like written as. And to that we subtract, or with this subtract it from our pKw, which is 14. So pH is pKw minus POH. So 14.00 minus 5.00. It's pretty easy. It'll give us 9.00 pH. So this will be our pH. So when it asks for the pH of a base, you kind of want to like do this. You want to write out the dissociation equation, make an ice table, and do all the things to find X, to find the hydroxide concentration. And from there, you can solve for POH, like I said right here, into pH. It's kind of the same thing for an acid. And asks you to find the POH of it. You kind of do the same thing. Wait, hold on. I forgot to write the ice here. Well, but yeah, always make sure you can do the simplifying assumption, because if you can't, that means you have to use the quadratic equation, and we don't want to use that. Or we want to limit our use like to as little as possible, basically. But yeah, that should be it for this question. Okay, number 5 says, for the following Bronsted-Lowry acid and water, write their balanced chemical equations and K expressions. So what this problem basically asks us to find or to do is write out their dissociation equation. So think of like the generic formula of an acid dissociating in water. Like this makes a conjugate base, conjugate acid, which is almost always, or it is always, hydronium. So this is kind of what we want to do to our acids we're given. So for the first one, I think this is dihydrogen phosphate, probably. That reacts with water. So water takes away one of its hydroxides, or its hydrogen ions here, and it becomes HPO4 minus 2, since it lost a positive charge, plus hydronium. And for the K, we basically just want to write that. So it'd be the HPO4 negative. Actually, hold on. This is balanced actually, so it's already balanced, right? Yeah, there's 1, 4, 2, 4 hydrogens, and yeah, it is balanced. So we don't gotta balance it further. Just focus on writing the Ka expression. Like I said in previous problems, we don't include the water because it's liquid. We only like include aqueous and gaseous things. We're not working with gases, so we just include aqueous things. This should be what you box. You could box this equation as well if you want, but Schultz would just see that and like automatically think that's what like you're giving him as your answer. But yeah. Now for B, Cl, CH2, COOH. I don't even know what this acid is called, so I'm not even gonna try. But let's just write out the dissociation equation. So we take away its hydrogen here. So it's Cl, CH2, COO, OO minus. Okay, so this is our conjugate base. And our acid, hydronium. I'm pretty sure this is balanced. I'm pretty sure they'll all be balanced, but you just want to make sure and count them. So one chloride, one chloride. All of this is already here. And there's five hydrogens. Yeah, so it is balanced. It's the same thing as the last problem basically, but the species change only, or only the species changes. So hydroxide or hydronium and our original acids, and we don't include water like I said, and this should be your answer. This is pretty easy. You just want to know what happens when they dissociate. They lose a hydrogen. The acids lose a hydrogen. What's left of them is a conjugate base. And the base being water here becomes a conjugate acid, which is hydronium. So it should be it for number 5. Okay, so 6 says a 0.017 molar solution of dimethylamine that has a hydroxide concentration of 6.14 times 10 to the negative 3 molar. Calculate its Kb. So this involves dissociating dimethylamine, which is a base. How do you know it's a base? Well, I don't really know, actually. But we're given a hydroxide concentration, which kind of implies we're working with the base because if you're working with an acid, why would you be given its hydroxide concentration? You'd more likely be given its hydronium concentration instead. So that kind of clues you into what you're working with. But anyways, we want to dissociate dimethylamine, so CH2. I'm sorry, NH. Reacts with water. Wait, hold on. Aqueous reacts with water, liquid. So this hydrogen gets. Actually, no. This hydrogen from here, one of them, gets stripped away from water and is given to the NH right here. So we're given CH2, NH3 plus aqueous and hydroxide. Aqueous. Let's make an ice table for this real quick. And we're given the hydroxide concentration, so we don't gotta work for that. And we'll treat that as our x actually. So plus x, so x. So since our hydroxide concentration is, what's it called? 6.14 times 10 to the negative 3. We'll treat that as our x. Molar. 6.14 times 10 to the negative 3 molar. So this starts off with 0.070 molar minus x. So we don't have Kb yet, which means we can't check to see if we can use the simplifying assumption. So instead, we just actually subtract x from it, which minus 6.14 times 10 to the negative 3. I'm sorry, times 10 to the negative 3 molar. And forget the molar here, but yeah, you get what I mean. So doing that gives us 0.06 0.386 molar. So not that big of a change from like our original concentration, but it's still a change. Yeah, so this is what we're gonna work with to find our KB. So our KB is our prior concentrations, which is just this. So since there's two of them, we could or like squares. Since they're like the same thing, basically, that's what I meant. Since they're two of the same thing, we could square them. And we divide it by what we just got, 0.6386. So that should give us a KB of 5.90 times 10 to the negative fourth. So this is our KB. This is pretty easy actually. You treat your given hydroxide concentration as your X, since you just set it as X. Like I said, how you know it's a base, you kind of want to like think of what you're given. You're given a hydroxide concentration, like why would you be given a hydroxide concentration if you were given with like an acid, So you kind of like think of it as that. So you're not working with an acid, you're working with a base because you're given the hydroxide concentration, not the hydrogen concentration. Well, that should be it for this one. Okay, so 7 says sodium hydroxide is used to clear clogged drains. A solution of sodium hydroxide has a pOH of 4.48 at 25 degrees Celsius. What is pH, hydroxide concentration, and hydronium concentrations? Okay, so this is pretty straightforward. You're given the pOH. So to find pH, you just subtract that from your pKw, which in most cases is 14. So 14.00, I mean. So minus our pOH, 4.48. Well, that gives our pH. Now for hydroxide concentration, it's just 10 raised to the negative pOH. So our pOH is negative 4.48. So that gives our OH concentration. And our hydronic concentration would just be um, 10 raised to our negative pH, which we're going to find right now. So doing all this should give us this. So you see, we got a pH of 9.52. We plugged it into this equation to solve for our hydrogen concentration, which is 3.02 times 10 to the negative 10. And our hydroxide concentration is 3.31 times 10 to the negative 5. And yeah, this should be it for this problem. Okay, so 8 says, write balanced net ionic equations for each reaction and label conjugate acid base pairs. So our first reaction is, let me just write it out real quick. NaOH, sodium hydroxide, reacts with sodium hydrogen phosphate. I think that's what it's called. To make water. And just sodium phosphate, I think it's called. Okay, so remember for net ionic reactions, we want to split up everything that is aqueous into the two things that make it up. Okay, so sodium hydroxide, that'd be sodium, the plus charge, aqueous. Hydroxide with a negative charge, aqueous. Sodium hydrogen phosphate, same thing, aqueous. And this would be, I think, hydrogen phosphate or dihydrogen phosphate, aqueous. Either way, water remains the same because it's liquid, it's not aqueous. And same here. Or not same here, but same for this aqueous compound. We split it up. So there's two sodiums here, which means you do 2Na plus aqueous and a phosphate ion. I think it's -3. Okay. I just realized I missed an H here, so we'll go ahead and like edit that after I finish this video. But it's sodium hydrogen or like monohydrogen phosphate, but he's right here, so it's -2. Sorry about that, but now we want to go ahead and remove all spectral ions, which means all the ions that didn't react. So you see, we got two sodiums here, and we have a 2Na here. So we get rid of those. And, oh, that should be it. So net ion equation is just our hydroxide, our dihydrogen phosphate, I think, our water, and our hydrogen phosphate. Oh, so now we want to figure out which ones are, or what our acid base pairs are. So you see hydroxide, that's obviously a base. What does that turn into? That turns into water. Because you get a hydrogen from here, you go to hydroxide, and it makes water. So this is a base. And bases make conjugate acids. And our dihydrogen phosphate is an acid because we already got a base here. So we just like automatically think it's an acid. And that makes a conjugate base. So this is kind of what you should put like as your answer. You kind of want to like indicate which one's which. Yeah. And if you want, you could like box them or something. Um, I think this should be fine. Like maybe box this entire thing if you want. But yeah. So our next reaction is potassium hydrogen sulfate. That reacts with potassium sulfite to make potassium sulfate. Oh, sorry, I misspelled it, but it's potassium hydrogen sulfite. It's a capital C instead of a capital S, but it's potassium hydrogen sulfite. So we're gonna split this up again, like the last problem. Potassium plus aqueous, and our hydrogen sulfate with a -1 charge, aqueous, and our potassium again with sulfite, which is just, oh sorry, it's K2, so it's two potassiums. Oh, the sulfite with -2 charge, so that makes two potassiums on the other side as well. And our sulfite, or sulfate, I mean, sorry, sulfate with potassium again and hydrogen sulfite. Oh, it says bisulfite, you could call it too, but it doesn't matter to be honest. It's the same thing. So now, obviously, the potassiums here add up to make 3 uh, on both sides, which means they didn't react at all. So we took those out. So our net ionic reaction would look like this: hydrogen sulfate plus our sulfite makes ester sulfate and hydrogen sulfide. So sulfate gains a hydrogen, which means it becomes an acid right here. So this is your base. Or I mean, it becomes a conjugate acid. Because it accepts a hydrogen, it becomes like a base. So by process of elimination, this is our acid, and this is our conjugate base. Which makes sense because we remove its hydrogen. You know, you remove a hydrogen from water to make hydroxide. That's kind of the same thing. So you remove a hydrogen from an acid to make a conjugate base. Um, same thing being shown here. So this is our acid. Let me fix our handwriting. Acid, not conjugate base. So you could box that if you want. And it should be your final answer. Okay, number 9 says a solution of propanoic acid with a formula of that made by dissolving 7.500 grams of it in 100.0 grams of water freezes at negative 1.890 degrees Celsius. It has a Kf of 1.86 degrees Celsius per mole. Find Ka. And that asks us to assume molarity or molality is equal to molarity. Okay, so this one is kind of unique because we're gonna be working with molality. And so you guys might remember this from last semester, or I mean last course for 150, but this change in temperature, freezing, is equal to the what's it called? The freezing point depression constant times molality. Lowercase m, not mass, molality. So it asks us to assume that molality is equal to molar. And to find Ka, we use molarities. Remember? So for K, we want to use the molarity of this acid. So we're going to be finding K with the standard like formula, like this. So to find all this, we first have to find the molarity of our acid. And to find the molarity of our acid, we have to find the molality of our acid, which is this right here. So let's go ahead and solve for that. So our change in temperature, we know our solution froze at negative 1.890 degrees Celsius. But what's our initial temperature here? Well, it's 0 degrees Celsius. Why? I don't know. I'm not gonna lie, guys. This problem is really dumb. And don't tell Schultz I said that though. I'm hoping he doesn't see this video actually, because I'm about to like BS my way through. So that would give us a change in temperature of 1.890 degrees Celsius. So to find molality, we just rearrange the equation to solve for that right here. So molality is equal to the change in temperature, freezing, sorry, over the, what's it called, the freezing point depression constant. So it's 1.890 degrees Celsius over 1.86 degrees Celsius per mole. So Celsius will cancel out, and we'll be left with mole, obviously. So that should give us 1.02. mole. Okay. And you think we'd use this like as our starting concentration, right? Nope. Wrong. Sorry, let me just like that. Okay. What we actually do is remember mole is moles of solvent, so of our acid, over kilograms of solute, so our water. We actually use this to solve for our starting molarity or molality. Sorry. So let me go ahead and do that for you guys. So this is what you get. You just divide the 7.500 grams of propanoic acid by its molar mass, which is 74.08. You get that. And you divide the grams of water by 1,000 to find kilograms of water. So this right here. Solve for the molarity. It should get us 1.012 molal. So they just 1.012 molarity or molar. Sorry. So with this, we're gonna make the ice table to solve for what's it called? Our Ka. So propanoic acid, the formula is CH3 CH2 COOH aqueous. So that reacts with water, liquid, to make CH3 CH2 COO. Gives away a hydrogen proton, or just like hydrogen ion, to make hydronium with water. Okay. So to solve for Ka, we need to find all three, like what's it called, concentrations. So all these two concentrations, this one right here. So our initial concentration, like I said, is this, not this one right here. No, that one's for later. Okay. So 1.012 molar minus x, 1.012 molar minus x. So we can't like use the simplified assumption right now because we don't know Ka. Okay, so 0, 0 plus x plus x, x, x. Okay, so this is where the like what's it called, mental gymnastics start. Okay, so for this problem, we assume that the concentration of our acid plus concentration over conjugate base CH2CO minus plus the concentration of our hydronium ions equal 1.02 molar. Don't ask me why, just just follow along, bro. Okay, so we can actually solve for x. Okay, because remember, this is x, and so is this. And this is 1.012 minus x. So if we expand it out, it's 1.012 minus x plus x plus x equals 1.02 molar. So let's look at it in terms of like addition and subtraction. Okay, so this minus x is cancelled out by this plus x. Okay, and we're just left with 1.012 plus x. We bring this x down. Equals 1.02 molar. Okay, now to solve for x, we just subtract this from both sides. I'll forget the molar part right here. Sorry. We just subtract 1.012 molar from both sides. So x should equal 0.008 molar. Okay. So this is gonna be our x, our what's it called, hydronium concentration, and our conjugate base concentration. So 0.008 molar and molar. Okay. Now for sorry. So from this we subtract 0.008. It's pretty simple, just like 1.004, I think. Yeah, pretty sure that's what it is. Okay, so now we have all of the components to solve for Ka. So Ka is just the concentration. Sorry. If you refer back to what I put earlier, is the concentration of our conjugate um base times the concentration of our hydronium ions over the concentration of our initial, like our acid. Yeah. So 0.008 squared, since they're two the same thing right here, over 1.004. Okay, so doing that should give us a Ka of 6.375 times 10 to the negative 5. In reality, it should be like 1 sig fig, since it's just 8 right here. But I just put it as 4, like following this right here. So this should be your Ka. I know this is like type of problem you've never seen before, because like when I saw this on my exam, I just left it blank, to be honest. But this is kind of like how like you should do it. Like if you were to see this problem on the exam, I can't say like for sure that you'll see this problem. Yeah, you're more than likely going to see this problem. So you should be familiarized with it, and maybe on the exam you won't be asked to solve for molality here. You might be given it. You might, like hint, hint. Okay, yeah. So, but the problem or the process, I mean, remains the same. You have the molarity right here. You don't use the one you solved for using like the change of temperature or the what's it called, freezing point depression constant. Instead, use the one you solved for using like what's it called, moles over kilograms. But yeah, the process is the same. Like I said, you solve for the molarities. The only thing that I would like what's it called, memorize is this thing, because this thing makes no sense if I'm being honest. But you might see it in the future. All right. But this should be it for this poem. Okay, number 10 says, imagine you have a 3.0 liter container of a strong acid solution and want to change its pH from 1.00 to 4.67. How many moles of hydronium and OH minus or hydroxide would you need to add to make it happen? Okay, so for this one, we want to find what's it called, the hydronium um ion concentration of each pH, and subtract those from each other to find like how many, or to find the change in like concentration. Okay, so let me okay, so since the pH is 1.00, to find the concentration of hydronium, we raise 10 to the negative power of that. So 1.00. Okay, that'll be for the first one. For the second one, it's 10 to negative 4.67. So that should give us 0.100 molar and 2.14 times 10 to the negative 5. So to find the change in that, we just subtract this by that. So 0.100 molar minus 2. 14 times 10 to the negative 5 molar. The change should be 0.0100. It was 9997, so I just rounded up from there, and you get 100 anyways, or like, let's go 1000. Like, hold on. So, oh yeah, it is 1000, right? Yeah. So it's really like approximate, but this should be about what like you should get. Actually, no, I'll write it out. 0.0999786 molar, and this will be hydronium, but it could be hydroxide too, because think about it. If you change this pH into a POH and find the hydroxide concentrations, subtract those two, you'd still get the same change. Or I hope you get the same change. So to solve for moles of hydronium, you want to start off with the volume we were given in the beginning. So 3.0 liters of our acid solution, and we multiply that by our molarity. Remember, molarity is um, moles over liters. You want to cancel out liters, so this would be on the bottom, 1 liter, and moles would be 0.0999786 moles of hydronium. So doing this should get you number of moles of hydronium of 0.30. I rounded to 2 sig figs since that's what we started off with here. So let me just put it there. That's kind of ugly. Like that. And it's moles of hydronium. So the problem says, like, what's it called? Moles of H3O plus or OH negative, because like either way you'll still get the same thing basically. Or I hope you get the same thing. But this should be it for this problem. It's pretty straightforward. You don't want to, what's it called? You don't want to subtract the pHs like right off the bat, because that won't get you the correct like um change in what's it called? Hydronium like concentration. Because remember, pH, every time you go up a pH, like 1, 2, 3, 4, you go up like tenfold in terms of like change in like hydronium concentration. So like if like a pH of 1 has like a number, like a set number of hydronium ions, if you go to 2, it'd be like that number divided by 10, because remember, pH goes up, hydronium ions go down. So you don't want to subtract it because of that. You want to find the concentration of hydronium first before you subtract the two. Yeah, so that should be it for this problem. Okay, number 11 says your lab partner makes 3 successive tenfold dilutions of 2.0 times 10 to negative 2 molar HCl. What is the pH of each diluted solution through 2.0 times 10 to negative 5? Okay, so making 3 dilutions, which means we need to find 3 pHs. So first we start off by diluting our 2.0 times 10 to the negative 2 starting solution into 2.0 times 10 to the negative 3, because we're diluting it tenfold, so we're actually working with our diluted solution instead of our starting solution, our stock solution. So we're working with our diluted solution, like I said, and remember, hydrochloric acid is a strong acid, which means it completely dissociates in the water. So we can treat this concentration as our concentration of hydronium as well. So for this first one, pH is pretty easy to find since our concentration is equal to that of our HCl. So it's negative log of 2.0 times 10 to the negative 3. That should give you a pH of 2.6. No, 2.70. So that'll be the pH of our first dilution. It'll be the easiest one. Now, moving on to our second one. So now we're going to dilute this one even more. And tenfold dilutions basically mean we're dividing it by 10. And this just divided by 10 is just 2.0 times 10 to the negative 4. So now you'd think we would do the same thing as this previous problem, right? But no, because now that we're diluting it even more, we're putting in more water. It's actually water that like is dominant over the like equation, okay? Or the reaction, I mean. So now we're going to be using an ice table to solve for the actual like concentrations. So since water is now dominant, instead of the HCl or hydronium, it'll be the reactant. And that is what makes hydronium and hydroxide. Okay, let's make this ice table real quick. So now we want to solve for X basically. And since water has taken over this reaction, instead of Ka or Kb, we use Kw. Okay. Remember Kw is 1.0 times 10 to the negative 14. I'm pretty sure. Yeah. So our initial concentration of this is just our initial concentration that we're starting with for the dilution equation, or for the dilution, I mean. So 2.0 times 10 to the negative 4 molar. 2.0 times 10 to the negative 4 molar plus x. And here's just x. So solving for Kw, we set up this equation. And remember, it's products over reactants. There's no reactants here since water is a liquid. So it's just our hydrogen concentration times our hydroxide concentration. That would just be 2.0 times 10 to the negative 4 molar. You just fix that. Plus x times x, which is just like hydroxide here. So we don't want to solve for Kw since we already know Kw is 1.0 times 10 to the negative 14. We want to solve for x. So let's just distribute these two first right here. So 2.0 times 10 to the negative 4 molar is times x. Plus x squared. So now we subtract both, or I mean Kw from both sides. So it's x squared plus 2.0 times 10 to the negative 4th molar times x minus Kw, and this should kind of like look like the quadratic equation right here. So this is our A, B, and our C. Okay, so now we want to set it up, which is kind of a pain, but it's your B or your negative B. So negative 2.0 times 10 to the negative 4. Plus or minus B squared. So 2.0 times 10 to the negative 4 squared minus 4AC. So 4A is just 1. C is negative Kw. and all of that over 2a. So just 2 times 1. Okay, so plugging that in should give us either x equals 4.99. Actually, hold on. It's 4 point. It's just 5.00 times 10 to negative 11, or x equals negative 2.00 times 10 to the negative 4. So obviously the correct answer would be this one, since it's positive, not negative like this one at the bottom. So this is going to be our x that we add onto our hydrogen concentration. So hydrogen concentration equals 2.0 times 10 to the negative 4 molar plus 5.00 times 10 to the negative 11 molar. And molar here. So doing that still gives me a really low number. It's like 0.00005 right here. Times 10 to the negative 4. I'm not sure this is really like even necessary. But this is how Professor Schultz wants you guys to do it. And on the exam, it'd be like an actual like higher number that Joe will be using. Not something really small like this. But something for the pH, it's just the same thing. So negative log. No, well, I'll still do 2.00. Actually, no, I'll do the whole thing. Times 10 to negative 4th. So that'll give me 3.70. And this is going to be an answer for the second one. So for our third dilution, it's basically the same thing. You just like dilute it even further. So now you're working with, what's it called? 2.0 times 10 to the negative 5 molar for your hydronium concentration. So we'll change that accordingly. So the same thing, or like same as last time, you working with water, since water is dominant in the reaction now. And making hydronium and hydroxide. There's 2 right here. So the ice table, the same pretty much. The only thing that changes, like I said, is the concentration. So 2.0 times 10 to the negative 5 molar plus x plus x. 0.0 negative 5 plus x. X doesn't change. Ice. So yeah, the same process. I'll go ahead and do it all for you guys, since it's kind of boring to just watch me. But okay, so doing that gets us a final hydrogen concentration of 2.00005 times 10 to the negative 5. Which, no, it's not that bad. Compared to our previous value, this isn't that bad. Like size wise, because there was like six zeros here. But yeah. To find pH, it's the same thing. So just log our concentration, so 2.00005 times 10 to the negative 5 should give us a pH of 4.698. So we should round that to 4.70. And that should be the first problem. I feel like you could like just skip all this and just like solve for pH from here. When I did that on the exam, I got marked wrong for it. So, or oh, no, I'm not saying this is actually on the exam, because I can't say that. But yeah. So if you guys are confused about this, I'll just study how to the method on how to find this, because it is kind of confusing. Because you've never seen water take over the reaction like this before, I don't think. So I'll just study it and get it down. But that should be it for this study guide video. If you guys have any feedback, just let me know. And I made a lot of typos on study guide, so I'll try to fix those as soon as possible and get it out along with the video. But yeah, have a good day, guys. See you tomorrow.